Good morning, everyone. Today we only have one presenter. We invite a PhD student, Guo Yongzhou, from the AIoT lab. His supervisor is Professor Li Zhenghao. Okay. So please welcome him, and then we can start.
Hello. Hello everyone. My name is Zhou Guoyong, and my supervisor is Professor Lin Zhenghong. Here's my email and contact information. Today I will introduce you the topic of fine-grained visual classification with high temperature refinement and background operation. And it's also a co-work with Gao Yong. Okay, here's my outline. First, I will introduce the fine-grained visual classification test and its background. Secondly, I will explain how related work is being done and their methods. Thirdly, I will show you our method first. Next, I will present the experimental result. Finally, I will bring out the conclusion. So what is fine-grained visual classification? It is concept that contrast with coarse-grained classification. Here, I show a figure to describe the relationship between these two concepts, coarse-grained and fine-grained. The coarse-grained visual classification test, also known as the traditional visual classification test, is defined as follows. It features large inter-class variance and small intra-class variance. For example, consider classifying between dogs and birds. Dogs are more similar to other dogs than they are to birds. Therefore, this test is relatively easy. Fine-grained visual classification, abbreviated as FGVC, features small inter-class variance and large intra-class variance, which is the complete opposite of coarse-grained. Let's look at these four bird species: the fair sparrow, grasshopper sparrow, and clay-colored sparrow, and blue sparrow. To me, they all look the same. This is what we call a fine-grained visual classification test. It's a difficult test. FGVC has some important real-world application, which is one of the reasons we choose the topic for our research. First is species recognition. By recognizing several natural animals, we can easily educate our next generation or provide useful information for those working in the wild who may need knowledge of various species, such as identifying types of venomous snakes. Second, it can use for model recognition to recognize different models of planes, ships, and cars. This can make inspection by the government much more convenient. Next, the third application is medical recognition. In the analysis of medical image, we often encounter situations where many photos look alike. And this is because they all come from humans. The photo all come from humans. Through fine-grained image recognition technology, we can enhance the stability and the interpretability of predictions. The image on the right is a collaborative project with National Taiwan University College of Dentistry used to identify types of dental implants. According to experimental results, using a fine-grained recognition model can significantly improve recognition accuracy. Okay, so how can we accurately classify fine-grained class? Here are two pictures from the CUB 200 2011 dataset. They are very similar. Let's think about how we recognize them. We need to identify the discriminative local areas, such as the area around the eyes or patterns on the wings. These discriminative features often classification. And why do we need a specialized fine-grained model design? And could we just use a vanilla backbone, and why does the vanilla visual classification backbone not perform well? Vanilla backbone include ResNet, EfficientNet, ConversionNet, or Vision Transformer. Here's why. Although these backbones perform very well in other image recognition tests, their design purpose is for general class benchmark like ImageNet. This method do not need to focus on small detail regions. On the following page, we will present two pieces of evidence to illustrate this. The first piece of evidence is that the model tends to focus on background, which should be irrelevant for classification. The image on the left, these two, shows the output visualizations of the swing transformer lodge, while the image on the right shows these two shows the result with the addition of the plugin module, which is a fine-grained module we have published. We can see that with plugin module is better at focusing on the object. The red area indicates confidence score larger than 0.95, indicate the semantic feature in this area influence the decision. So swing transformer large backbone will focus on background, but it's not great. The second piece of evidence involves using GradCam to directly observe the feature map's response to the predict category. GradCam results show that the fine-grained module can force the model to focus on sector area, like this one. The image displayed here are also from swing transformer lodge, and the result after adding the fine-grained module Hertz. You can see that after adding Hertz, the focus on the object is enhanced. So only use backbone module won't work well on the fine-grained test. How do we implement the fine-grained module? Historically, there have been three main approaches. The first type is object path based. The second is attention based, and the third is self-attention based. As illustrated in the diagram on this page, the first approach here use a region proposer to identify important location on the feature maps and then recognize it. The second approach use attention mechanism to identify relative position or to enhance positional features. The third approach use a self-attention map to get important location. The object path-based fine-grained module can be divided into two types: cropping the original image here, and cropping the middle feature. There are several approaches to obtaining region proposal. The most famous and effective being the class education map, or CAM. Alternatively, you could train an object detection model, which, however, is not allowed in our test. We cannot use the bounding box label. Attention-based model can be also be divided into two types. The first type focuses on the attention within a single input, which is commonly used to enhance its own features. The second type uses attention across multiple inputs, allow for comparison of similarity and difference in various photos, like this one. We use two images and calculate the attention between the middle features, and we can get the background and the foreground area. The third one is self-attention-based model, and it can also be referred to as transformer-based model. By utilizing the self-attention mechanism within transformer to generate an attention map, it is possible to identify which page are more important. This allows us for enhancement to fine-grained features. Like this, we can use self-protection map and choose the important one, and then send the important feature to classify and make a great, more fine-grained prediction. Okay. After discussing this test approach, let's now address some issue with this method. This is a basic predicting flow of fine-grained visual classifications divided into 3 steps. First, backbone forwarding. Second, feature selection. And the third, fine-grained feature extraction. In the second step, they only use selected features, which focus attention on select area and fail to limit the performance of area not selected. In the third step, they only use single-scale features or average features from all scales, treating them as equally important. This approach does not effectively utilize features of varying scales, which is particularly crucial in fine-grained tests where the feature scale should be important. To overcome these 2 problems, we propose the background spatial module and the multi-scale combiner. I use blue text here to represent the background spatial module. Areas that were not selected should be forced to predict a background signal. This technique would provide more effective noise reduction. And I use green text here for a multi-scale combiner. It dynamically aggregates features from different scales using a graph convolutional network. With these 2 modules, we can efficiently remove background noise and merge multi-scale features. Another problem with fine-grained visual classification test is that it tends to fine-grained module. The other problem with fine-grained module is that it tends to filter out excessive information on the feature map. This is because most fine-grained algorithms designs treating anything not belonging to the target category as background. However, sometimes these features should be used for origination to prevent the model from focusing on areas that are either too large or too small, and to avoid excessive or insufficient emphasis on semantics. This concept suggests that good features can be used to assemble high semantic content and produce accurate results. For example, like backward backup features. However, deep network may overfit to the ground truth in the final layers, leaving a very high semantic precision but excessive focus. So here's what we do. The model is forced to learn deep fine-grained feature at shallow layers, incorporating disturbance into the learning target. This approach enables the model to explore relationships between different categories within a defined range as much as possible, allowing for broader development of features on the feature map. As a result, the feature in the earlier layer will not be dominated by response to single category. Let's take a look at the final result. These 2 images are successfully recognized only when the Herbst module is added, which means it captured just the right information by Herbst. Middle is the other fine-grained model, and the first is backbone. Vanilla backbone focus on too large, other fine-grained too small, and Herbst is just right. Here are 2 main contributions of this research. The proposed Herbst can be integrated into various backbones, such as convolutional-based networks and transformer-based networks, and it allows for end-to-end training. And the second one is the proposed Herbst outperforms state-of-the-art approach, improving accuracy to 93.1% and 93% on CUV200 2011 and enable dataset. In this chapter, I will introduce several methods incorporated in our Hobbes model. We focus on these four techniques: multi-scale feature extraction, feature selection, feature fusion, and deep supervision, which could be achieved by refinement and distillation technique. The structure of feature pyramid network consists of two main pathways. The bottom-up pathway, here, this way, which is typically fit for work architecture in convolution network, and the top-down pathway, here, which allow higher resolution information to be smoothly merged into low resolution but semantically stronger feature from higher layers. And here is the method of merging. And class attribution map. Class attribution map generates heat maps that highlight the importance area in an image that contribute to classifying a particular object. This is achieved by mapping the weight of the output layer back to the convolutional layers, creating a visual representation of the areas that influence the model's decision. This method not only enhances our understanding of how neural networks make decisions, but also improve the interpretability of model predictions, making class activation map available for both model development and applications requiring explainability. We utilize graph convolutional neural network to combine features across different scales. To understand GCN graph convolutional network, one must first know about the graph data structure, which consists of two parts. The first part is the data point, like circle 0 to circle 3. And the second part is adjacency matrix that describe the relation between these data points, like I show here. Data point 0 and data point 1 have a connection, so we mark 1 in adjacency matrix here, and 0 and 3 connection, so we mark 1 here, to describe the graph relation. Okay, and the operation of GCN can be understood as follows. Each data point performs a 1 multiplied 1 convolutional operation. In other words, it is fully connected at each data point. Then features are fused according to a specific relation defined by the adjacency matrix. Through this process, we can effectively combine features from different scales. And knowledge distillation. This method involves transferring knowledge from a large complex model, often referred as a teacher, to a smaller, more efficient model called a student. In this case, model A is teacher, model B is student. The goal is to help the student model learn to perform tasks at a level close to the teacher, but with reduced computational cost and model size. By distilling the teacher's knowledge, we can deploy powerful AI models in more resource-constrained environments, enhancing accessibility and efficiency. And model A and model B can be in the same model. The model A could be a deeper one, deeper layers, and model B shallow layers. In this situation, we will call it self-distillation, and can be useful for us to constrain the information flow in a fine-grained model we discussed earlier. Okay, through the techniques mentioned above, we can design an effective fine-grained model, and is our proposed Hobbes module. Let me introduce what is Hobbes module. First, this image shows the entire architecture of the model, which mainly consists of the backbone, model scale feature fusion, multi-scale feature fusion module here, and subsequent selector and combiner. Okay, selector is a green one, and combiner is a yellow one. Okay, selector is used to choose which feature should be combined by combiner. Okay, and later I will explain the entire forward process. The first step involves the forward operation of the backbone. This backbone could be any types of model, including convolutional based or transformer based models. Then the second step is to fuse multi-scale features. Is to fuse multi-scale feature maps and make a class prediction for each of them. So if we choose Resonate 50 or swing transformer as backbone, we will have 8 class prediction in this step. Because swing transformer 50 and Resonate 50 and swing transformer have 4 blocks, and each block has 2 stage output, stage 1 and stage 2, so we have 8 class prediction. The third step involves using the selector to choose stage 2 feature. Stage 2 feature here. Choose stage 2 features based on the stage 2 classified content score. We also gather features from unselect areas, which we refer to as dropped features. So in this step, we have select features and drop features. Finally, the fourth step involves the combiner using a graph convolutional network to combine select features from different scales and make a class prediction. How does a selector choose features? The upper part of this figure illustrates the operating principle of the class activation map selector, while the lower part shows our selector. Each pixel on picture map enter the classifier to obtain classification result. After applying softmax to this result, we take the maximum probability value. If this probability value is high enough, it will be selected. Otherwise, it will be dropped. The difference between the two methods is that can select only the highest classification output, only use one class, whereas our method allows each pixel to have different class prediction. This benefits us by allowing the model to learn more diverse semantic features. And the combiner is composed of graph convolution network. We do not predefine an adjacency matrix. Instead, we generate it dynamically. The working principle involves using self-attention to find a self-attention map here. Learnable adjacency matrix is added into a self-attention map. This learnable adjacency matrix can be seen as a form of prior knowledge that stores the relationship between scale features through learning. The final adjacency matrix we use is the sum of these two matrices, self-attention map and adjacency, and learnable adjacency. After discussing the forward process, let's now talk about how to optimize the model. First, let me introduce 3 types of loss function. The first type is the cross-entropy loss, commonly used in supervised learning. The second type supervises the output of one classifier on the output of another one. This one supervises this one. This is a method belonging to self-refinement, or you can call it self-distillation. The value of this loss is determined by calculating the similarity between the outputs, using KL divergence as a method for measuring similarity. And the last type involves supervision, the background portions. We define the background classification target as zeros, meaning the model should output the signal. I don't know which category this is, 0. Okay. If the model output of 0, it means the model doesn't know which class it is, so it's background. Okay. We use ground truth target for these 4 layers. stage 2 output. Okay, these 4 layers output we call stage 2 classification prediction. And we call the loss stage 2, and we will multiply by lambda stage 2. The second loss is loss refinement. We use stage 2 output as a target for stage 1. Okay. This one's output to supervise this one. This approach enables the model to explore relationship between different categories. And the third and fourth loss, the classification results of the drop feature are supervised by 0. Here, we call it loss drop, and we multiply by lambda drop. And the combiner is supervised by ground truth here. We call it loss combiner. We will multiply by lambda combiner. Okay. Here we have the entire loss calculation. Here, we just sum all. We use different ratio, which means different lambda values. With this, hooks can be trained directly in an end-to-end manner. Okay, here is my introduction to high temperature refinement and background suppression module. And let's see the experimental result. Our model achieved 93.1 on the CUB 200 2011 dataset, beating a previous state art by 0.7% and scored 93% on the NA-first dataset, which is 0.3% better. It's worth mentioning here is Metaformer use, this one, use RGB images with geometric information as input, and we only use RGB image. Next, we analyze the accuracy improvement followed by different components. PA here and here. We present the multi-scale feature fusion module. PA is abbreviation of PACE application. And refinement indicates supervision stage 1 through stage 2. And BS represent the use of selector, combiner, and background suppression. From table 2, it can be observed that the swing transformer base achieved a total accuracy improvement of 1%. And showed improvement in each group after incorporated. Similarly, the swing transformer large achieved a total accuracy improvement of 1.1%. And moving on table 3, it can be seen that even on convolutional based methods such as ResNet 50, there is also an improvement with a total accuracy improvement 1.6%. Next, we set experiments on the structure of component, combiner. The experimental results discussed here are based on the incorporation of multi-scale feature fusion into a backbone, and the method used by combiner. The reason for not including all modules is due to the consideration regarding the training time. And we can see graph convolution network is better than multi-layer perceptron and just some of it, just averaging. And then we evaluated the performance of hooks on real fine classes in the CUB 200 2011 dataset, which contains about 70 generic classes with 1 to 25 subcategories each, including 9 generic classes with more than 6 subcategories. Table 4 lists these 9 generic classes, and we evaluate the model's performance on them. The results show that Hertz outperformed the swing transformer baseline regarding false precision and false positive number. False positive number refer to class where the model predicts a class that does not belong to the correct genetic class. A lower false positive number means that wrong prediction occur within false positive Number refers to case where the model predicts a class that does not belong to a correct generic class. A lower false positive number means that wrong prediction occurs within a similar category, indicating that the model is not making serious mistakes. For example, doctors can trust the results from a fine-grained module and only need to check similar situations, reducing the effort required for double checking. Both precision rate and false positive number is better than the baseline. And here's why we set the temperature parameter relatively high. We experimented with temperature range from 0.5 to 256 and find that the highest accuracy occurred around 64. We hypothesized that this is due to the approach enabled the model to explore relationships between different categories within a defined range as much as possible. To support that hypothesis, we analyzed the relation between false true rate and top one accuracy. False true rate means model predict a wrong answer in a stage 1, then make it right in a stage 2. A higher false true rate corresponds to a higher top one accuracy. You can see the top left one, this one. You can see this figure. This means encouraging the model to explore is beneficial for fine-grained visual classification tests. And then we test the separation intensity, lambda D, lambda drop, from 0 to 9 and plot their corresponding heat map in this figure. From the heat map, we observe that when lambda D is set to 0, which means only the combination loss from select area is used to constrain the feature map. The model still pay attention to some background area. This one. And comparing the heat map of lambda D at 0, 5, and 9, we observe that the concentrate level increase as the separation level increase as lambda D increase, demonstrating that the BS module can effectively suppress background noise when the lambda D increase. We further investigate on the growth and decline of receptive files and present the 5 stages of our experiment. We test the original backbone as shown in upper here. This is backbone, and its corresponding heat map is here. It was observed that the model paid attention to a large amount of background area, indicating that the original backbone is not designed for detecting detail in fine-grained data. And we add a classification multi-scale feature fusion module, and then add 4 classifier, add 8 classifier, and then add our first module. This one is corresponding to this one, and this one is one. And the result demonstrates that Herbs achieve better accuracy. And in this example, only Herbs predict the image correctly, while the other model predict the images to a wrong but visually similar class. This demonstrates that fine-grained visual classification requires balanced detailed features rather than features that are too narrow. Okay, here is our conclusion. In this research, we propose Herbs with high temperature refining module and background separation module. And it can improve accuracy to 93.1% and 93%. And for different classification tests, future works explore the use of adaptive strategy to select temperature parameters and background separation intensity based on Herbs. Okay. thank you for your attention.
Thank you for your presentation. So may I open the floor to the questions? Any questions? Any questions? No? Okay, so thank you for your informative application. I learned a lot from you. The presentation begin at introducing coarse visual classification and the fine-grained visual classification, right? And then you also introduce us some techniques. Then actually I'm not the man in the field, but what I know about the fine-grained visual classification is the duty of the technique integration. So I mean, ranging from how to create the balanced data set, and then in order to achieve that, you may need to do some data augmentation and also to do the pure shot learning. Yeah, and then you may need to carefully select the backbone. Yeah, after that, you will have to to do some training. Then the training you may meet some problems of overfitting. So you have to think about something or you may apply like a batch normalization or something to avoid it, right? Then after that, you have to choose like a proper matrix and also have to fine tune your parameters. Yeah, and then listen your presentation, and this moment is still unclear to me how you fine tune the parameter. This is question number one. And second one is like what? Have you ever conduct the evaluation test? Yeah, to have the evaluation test, is try to know what are the factors which may contribute most to the final result. Yeah. So these are question number one and two. The third one, yes, I realize you use the top one, right? And what I know about image processing, sometimes you try to evaluate the performance, you may choose top one or top five. Yeah. May I know why you choose top one?
Okay.
So there are three questions.
Okay. First question: how we transfer learning from pre-trained model? We use a small learning rate, and it worked well. If you use large learning rate, it won't work well. So we just set a smaller one, like 0.0005 as an initial learning rate, and it will decay while we train it.
So learning rate will be the key factors.
Yes, one of the key factors.
Okay. So then what else? I mean, yeah, have you conduct like the comprehensive analysis on the factors?
Yes, training a fine-grained model has a lot of things, a lot of detail. You need to a lot of hyperparameter. You need to set it right, like learning rate and weight decay. Yes, I should this all, yes, but not this.
And then have you ever conduct the evaluation test?
Yes, but we are not presenting our papers because we think in this field, everyone do a similar setting.
Okay. And then about is there any reason why you choose top one as
Oh yes,
sure.
If we choose top five, every model we compare will be 100% accuracy.
Okay.
So I choose top three here, but it's not important. It just help me to describe the fall through rate, because top three figure is same as top one figure in
You mean the top 1 and top 3?
Yes,
The trend will be the same.
the trend will be the same.
Okay. Right. Okay. So, any questions? Any questions from the floor? Or will we have this student live? But you can question him something about the deep learning technique, right? Okay. So, any questions? Okay, no questions. I think we can end today's session since today we only get one presenter. Yeah, so thank you for your presentation.